So we've talked about precipitation reactions, and those are reactions which occur by double replacement. We have two ionic compounds. Those two ionic compounds exchange cations or exchange anions. Either way, it's the same result. And then what you end up with is two more ionic compounds. Now, in this same group of reactions, we have what are called acid-base reactions and gas evolution reactions, and these are the ones that are covered in your book. So, in an acid-base reaction, you have two compounds which consist of positive and negatively charged parts, just like the cation and the anion. And what ends up happening is they exchange partners, and we end up with water and another compound, which is the technical name for the ionic compound that's produced by these reactions, is a salt. So the word salt that you learned as table salt, for example, NaCl. Looking at my pen to write. There we go. NaCl really comes from the reaction of NaOH, which is my base, and HCl, which is my acid. When those two get together, we do this double replacement. So we switch like this. We get H2O. And then the other product of this reaction would be NaCl. And that's where that is. Like that. Okay, so that's an example of an acid-base reaction. Again, it's very similar to a double replacement reaction that you learned for precipitation. It's just that the products aren't solid now. Sodium chloride is aqueous and H2O is a liquid. And one of the things to point out is the reason this reaction takes place is because water is a very stable molecule. And so by reacting the sodium hydroxide and the HCl, we can produce this very stable water molecule, which helps to make this reaction go to completion or towards the forward direction. We call another name for the acid-base reaction is a neutralization reaction. In a neutralization reaction, the way we're thinking about what's happening is acids have certain properties, which we've talked about before, and bases have certain properties, which we again talked about before. And when you mix them together, some of those properties go away. So in that sense, they neutralize each other's properties, and that's why it also is called a neutralization reaction. Now, gas evolution reactions are also very similar to precipitation reaction. Only difference is, right, like in an acid-base reaction, the product's not a solid. In a gas evolution reaction, what comes out is a gas. Okay, so again, classified in the same group, it's done by a double replacement reaction. Many of them are acid-base reactions, but because they form a gas at the end, we classify them slightly differently. There's 4 of these, which we'll go over, that you need to remember and be able to predict that the gas that's formed from the reaction. But again, it's a double replacement reaction. It's the only difference is one of the products is a gas. So let's talk a little bit about acids and bases, and there are several different definitions of acids and bases, and the one that we'll use in this class primarily is the Arrhenius definition. An acid is something that produces H plus when added to water. So what Arrhenius recognized is things that have the properties of acid, what they're actually producing in water is H plus. Now, here's the thing about H plus. H plus is what? It's a proton, actually. Because remember, hydrogen, right, has 1 proton and no neutrons. The regular hydrogen, we'll call it that. And a 0 charge, it would have 1 electron. So if you make H plus, has no electrons. Well, it turns out a positive charge, like a proton, can't exist in the solution very stably. So what in fact happens is the H plus recombines with a water molecule to produce hydronium. And hydronium looks something like this if water looks something like that. So this is H2O. This is H3O plus because it picked up that proton that the acid got rid of. And so in a sense, this is the actual final product of an acid-base reaction. Now, we classify acids as either strong or weak, and we talked about this earlier. Strong acids completely dissociate, and we talked about acids when we talked about electrolytes, if you want to go back and look at that. But we talked about acids as being strong or weak, and the strong acids completely ionize. So that means they 100% break apart into the hydrogen ion, or in this case now hydronium, and the chloride ion. We also have weak acids. Weak acids don't completely dissociate, and there was a list of strong acids that I was telling you to memorize, and those are things like HCl, HBr, HI, HNO3, and H2SO4. Those are perchloric, HClO4. And there are others, but for those are the ones predominantly that would be used in this class. And when you see those, you need to recognize that they're strong acids and that they completely dissociate into the cation and the anion. Then there's weak acids. Weak acids are everything that are not in this list. So this is the strong, and everything else is weak. Okay. Now, there are things called polyprotic acids. Now, if this is a proton, then a polyprotic acid simply has more than one hydrogen, and those would be acids like H2SO4. The first ionizable proton, this is what it means by that, it forms the ion, right? The first ionizable proton is the strongest, and subsequent ionizations are weak. So actually, when you look at sulfuric acid has a strong first ionization, and then it forms hydrogen sulfate and hydronium. This is 100%. And then HSO4 minus can also undergo ionization to form H plus or hydronium and SO4 2 minus, but this one is not 100%. And typically, it's around 10% for the second ion. This is known as the second ionization reaction, because it's the second of the hydrogen ions to be released from the compound. So that's kind of a summary of acids and how they behave in water. So what we'll do next is we'll look at some bases. Okay, so a base in the Arrhenius definition is something that produces OH minus in solution. In fact, the way that you recognize an Arrhenius base is it actually has OH as part of its formula. It's a metal hydroxide, so that first thing has to be a metal. And then this is hydroxide, which you're probably familiar with. But you can also have, for example, as in the example down below, you can have a dibasic ion, one that has two hydroxides in it. And you can also have bases that we'll be looking at that don't fall into the Arrhenius definition, and those are amine bases, and those are NH3 type or NH2 type of bases. You have a nitrogen and some hydrogens, and then the nitrogens in this case is bonded to something else. So these are another classification of base, and I'll go over those in a little bit because we do encounter them quite a bit in this section. So an acid-base reaction we call neutralization because the acid and base neutralize each other's properties. Here's an example of an acid-base reaction. There's nitric acid reacting with calcium hydroxide, and you end up with calcium nitrate. This is the salt of the reaction. And water. So water is always one of the products of the reaction. Now, one of the things I think that's useful to sort of see and have pointed out to you is that since one of the products is water, you notice there's an OH here and there's the H here. As soon as you see that in the reaction, you know what the stoichiometry is because there's two OHs down here. there's going to have to be 2 nitric acids to make 2 water molecules. And that actually really helps in predicting what the products are and what the stoichiometry of the reactants are. We are often using these balanced reactions in titration reactions, and really all we care about is the reactants of the reaction, so we can do our stoichiometry of our titration. Now, let me talk a little bit about amine bases. So, give you an example. Here's methylamine. CH3 is known as a methyl group. NH2 like this. And it has a lone pair on the nitrogen. And then it can react with water. And when it does, what it does is it steals the proton. Remember, this is a proton. From the water and forms CH3. And I'm going to draw it like this, although you wouldn't normally see it drawn out like this. NH2 plus OH minus. So stealing the proton, this is the proton here, which actually forms a bond on the lone pair of the methylamine nitrogen. Right? So that's this pair of electrons here. Let me put them in a different color. This pair of electrons here is actually this pair of electrons here. That bond, right, removes the hydrogen from the H plus, removes the H plus from the water and leaves me with OH minus. So there are other ways to make solutions basic when you put something in water. But this is actually turns out to be a different definition, but I just wanted you to recognize that that's what an amine base will do, and it produces hydroxide in that kind of reaction. So here's a list of acids and a list of some common bases. I wanted to point out to you these. This is out of your, went too far. These, the ones that are in black, are the strong acids that are recommended that you memorize. And then some of the more common weak acids that are shown are down here. So you notice they list those as weak. Weak acids are the ones that aren't strong. So in this studying this chapter, then all you need to recognize is these ones, and everything else is weak. Okay. Now the other thing is they do list ammonia down here, and they list the reaction that we just went over for making an ammonium type ion. Remember, we talked about amines in chapter 2 or so, maybe chapter 3. We talked about amines in that chapter, and we talked about now we've talked about how an amine can react with water to form ammonium ion and hydroxide, but I should point out this is also known as an ammonium ion, but it's a methylammonium ion. So the last bit is just referring to the positive charge on the nitrogen and the extra hydrogen that it's picked up. So this is what we're going to do. We're going to do some practice balancing of the reactions, but we have to also predict the products. I'll do the first one, and then I'll pause the video, and then I'll let you guys take an attempt at the second one. Now, I do want to point out that in reaction number 2, that this substance here, right, is acetic acid. And at first, people, when you first are starting to learn chemistry, you have a hard time recognizing the acetate ion that produces the acetic acid. So this whole thing, when this breaks apart in water, it's going to form H plus and then eventually hydronium, and then C2H3O2, and then minus. So this whole thing stays together, so don't break that up as you do it. The same thing is true for formic acid. It'll split there, and HF is easy because it's just HNF, but they also split there. So in the definition, or in the structure of the acid, that first hydrogen that we put in the formula in Chem 1A is the ionizable hydrogen, and then the rest of it breaks off altogether as one piece, okay? So with that, we'll go ahead and do reaction number 1, and the way you would do it, at least I think I would do it, I would say first thing, that's an acid, and that's a base, so I know my one product is water. So that's a given in these reactions, that you'll have water as a product. Now, the other thing that you do is you look at the metal ion that's here, and the anion that's here. It could be polyatomic, it could be monatomic, right? But barium, what group is it in? Well, it's in group 2, so I know it has a 2 plus charge. Now, had I forgotten that, I could have guessed that it was 2 because that's where that 2 comes from when you're writing the formula of the compound. The other ion is chloride ion, and based on its position in the periodic table, I would have predicted it has a -1 charge. And so my other product is barium chloride, like this, okay? And then you need to balance it. But the easy thing to do in the balancing is recognize you have 2 OHs here and 1 H here, so I'm going to need 2 HCl's to produce 2 waters, like that, okay? So those little clues in the structures of the compounds make it really easy to balance these reactions. So this is what you'll do, is pause the video and go ahead and try to do number 1, and then I'll have it worked out and we'll talk through it. Okay, so first thing I did was I said, okay, I have an acid and I have a base, right? I have H plus and OH minus, so that's going to form water. Now you notice in the formulas there's just 1 and 1, so I already know before I even have predicted the other product, because there's only 1 hydrogen, only 1 hydroxide, the stoichiometry will be 1 to 1. And so I'll get 1 molecule out, water molecule out, and now I predict the other product. So aside from the OH minus, I have potassium ion that's here. Oh, my mouse died on me. I have the potassium ion that's here, and then I have the acetate ion, which is what's left after the hydrogen is ionized, and that allows me to see there's +1, -1. Metal, cation always goes first, anion always goes second. Now, I did also want to point out one other thing that I just realized that maybe isn't obvious still, so I'm going to do this. If I split the line there and I know this is +1, then I know this is -1, right? So it goes back to the naming of ionic compounds in writing the formulas of the ionic compounds. If you put a line between the cation and the anion, you know the charge on the left and the charge on the right of that line have to add up to be 0. So for example, if I know that this is +1, then I know that this is -1, like that. Okay? So that's how you do acid-base reactions. So it could be any acid, any base, always produces water as one product, and then you look at the ions that are left and you can predict the ionic compound. That's the other product. And the other thing that's very helpful to recognize is that the numbers of hydrogens and hydroxides in the compound are giving you an idea of what the stoichiometry of the reaction is, and so it makes it a lot easier to complete the reaction and balance it.